Okay, so problem 8.31. Draw the graph of the following functions. Okay, so this is the same as the previous problem, it's just that these functions are more complicated. Okay, but yeah, we're gonna see how to do them. Okay, so first of all is f is the minimum of the logarithm of the absolute value of x cubed minus 3 and the logarithm of x plus 3. Okay, now so we have two functions here. First, the logarithm of this, which is a bit complicated. The logarithm of x plus 3 is the same as the logarithm of x, right? But instead of having the 0 at 0, it has the 0 at minus 3. Okay, so let's draw a vertical asymptote here at minus 3, right? X equals minus 3, and so we have the absolute value of this. Let's see, this is 0 at x equals sorry, the argument of this is 1 when this is 2, right? So 2, wait a minute, minus 2, yes, sorry. So minus 2 here, right? So we have the logarithm just doing something like this. Well, let me paint it again. That's something like that, right? And then notice that this is the absolute value of x plus 3. So this is going to be an even function and symmetrical around x minus 3, so something like this. Okay, well, if I ever learn to paint, it will be something like that. Okay, now what happens with the logarithm of the absolute value of x3 minus 3? Okay, now let's see what the roots of x cubed minus 3 are. So x cubed minus 3 equals 0. It has obviously one root, which is one obvious root, which is the cubic root of 3, right? Now if you divide this by the cubic root of 3, what you have is a parabola, which is something like x squared plus ax plus b, right? And this kind of parabolas are not going to have any more roots. Okay, the ones, if you get it, so this is going to be x cubed minus 3 is going to be equal to this, right? So actually in this case we can actually use our formula, right, that we have used before. X cubed minus 3 in this case is the cube of this. It's going to be x squared plus the cubic root of 9 times x plus the cubic root of 3. That's what the parabola is going to be, right? Now if you try to find the roots for this, you will realize there are no roots. Okay, so you have minus 4 times this, and this is greater than this square. So there's no real roots of this. So there's only one root of this, which is going to be the cubic root of 3, which is approximately 1 point something. Okay, so this is x equals 0, and this is the cubic root of 3. Okay, so the logarithm is going to be going to go like this and going to go like this, right? But also now we want to see where is this, maybe see if it has extrema or changes of inflection, things like that, right? So then we have g, let's call g the logarithm of x cubed minus 3. Now g prime is 1 over x cubed minus 3 times the derivative of this, which is 3 squared over 2. Now this has valued 0 at 0 only, right? And so then what we have to see is that the derivative is going to be greater than 0. Let's see, this is positive both at the left and the right of 0, and this is negative both at the right and the left. So the derivative is going to be negative. It's actually going to be negative everywhere left of the asymptote, and it's going to be positive everywhere left of the asymptote, right of the asymptote, sorry. So this is an inflection point. Okay. Now if we want to compute the second derivative, this is going to be x cubed minus 3 squared times 6x x cubed minus 3 and then minus 3x squared times 3x squared, so this is 9x cubed, x first, sorry. And this is equal to 6x to the 4 minus 3x to the 4th minus 18x divided by x cubed minus 3. Okay, so this is minus, and then we have 3x times x cubed minus plus 6, okay, divided by x cubed minus 3 squared. Okay, so the denominator is always going to be positive. Then we have an inflection point at 0 and an inflection point at the root of this, which is minus the cubic root of 6, or the cubic root of minus 6 if you want. It's the same thing. And so this is going to be somewhere here between 0 and minus 3, right? The cubic root of 6 is going to be smaller than 2. And yeah, this again, this cubic polynomial doesn't have any more real roots, okay? So let's say this is going to be, let's see, this is positive, right? So when this is negative, when x is smaller than the cubic root of this, positive, so let's say it's something like this, okay, cubic root like this, let's say, and if this is the cubic root of 6, it will be like this. Change the convexity, and then at 0 it changes again, right? So it's concave, convex, and then concave again, something like that. And then for positive x, after this it's going to be concave, and so it's something like that. Okay, so that's this weird curve that I don't know how to paint is the logarithm of the absolute value of x cubed minus 3, and then the other one is the logarithm of x plus 3. So the minimum is going to be this, okay, and then this, then cut here, right, and then this here, and then cut here, okay. And maybe you want to find those points where the two values meet, okay. So you need to find where the absolute value of x cubed minus 3 is the same as the absolute value of x plus 3, because the logarithm is an injective function. But yeah, for this we don't really need to do it, okay. Okay, let's do part 2. So part 2 is f is equal to 1 over the absolute value of x minus 1 minus 1 over the absolute value of x minus 1. Okay, and so let's see, there's like different behaviors of this depending on the values of the absolute value. So if x is, let's say, if x minus 1 is greater than 0, so that means that x is greater than 1, right? Then f is 1 over, this is positive, x minus 1 minus 1 over x minus 1, f is 0. Okay, now if x is between 1 and 0, then this is 1 over x minus 1 plus 1 over x minus 1, right? You change the sign here. So you have 2 over x minus 1. And then if x is smaller than 0, we have f is 1 over minus x minus 1, or minus 1 over x plus 1 if you want, minus 1 over, this is the same, x plus minus 1, okay? So you can compute this using the product of the denominators. You have x squared minus 1, and you have, this is minus x plus 1 plus x plus 1, 2. Okay. Okay, so now let's compute this thing. So let's plot this. Now if this is x0 and this is x1, okay? X equals 0, x equals 1. If x equals 1, greater, f is 0, right? Now if it's between 0 and 1, then this is 2 over x minus 1. And then, so let's say at 0, this is going to be minus 1, okay? So this is minus 1. This is the value. And then this is going to, this, as you can see, this is 1 over x minus 1 times 2, right? So this is an inverse function with the asymptote at x equals 1, so this is just going downwards like this. Okay, well, if I had painted this asymptote correctly, wait a minute, okay, you have this. You can always watch this functions properly painted in the lecture notes, okay? And now then we have what happens at here. It has two asymptotes. You see, this is the sum of two inverse functions. So this is an asymptote here at minus 1, right? So at minus 1, right, so this is, if we paint these two different things, right? So we have 1 over x minus 1 is going to be like this, right? And then minus 1 over x plus 1 is going to go like this, and like this, right? So this part, this is x minus 1, and then this is x equals 1, and in the middle you have 0. Now when x is negative, smaller than minus 1, you have this subtracting this, but this is going to be very small already, okay? So you don't really notice this. This is something like this, okay? And now here you have this minus this, you get something that's going to minus infinity, okay? So it's something like this, okay? If you want, you can check that the value at 0 is going to be minus 2 again. Okay, this is minus 2, and then we would need to check that the function is differentiable here. Okay, so let's see, the derivative of this function, let's say this is f1, f2, and f3, so this is the derivative of f1 would be minus 2 over x minus 1 squared, and at 0 this is minus 2, right? And then the other one is this, sorry, this is 2 and this is 3. The derivative of this is going to be 2, and then divided by x squared minus 1 squared, and then minus 2x, right? So minus 4x, x squared minus 1, 0, x squared, right? If I'm correct. And so yeah, this is the derivative at 0 here is 0. Is correct? So this function, yeah, so there's a discontinuity here, okay? So we're having this on the left, we have in this, okay? And on the right we have this, okay? Let's do part 3. Part 3, you have f is equal to 1 over 1 plus the absolute value of x minus 1 over 1 plus the absolute value of x minus a, when a is greater than 0. Okay, so again, we have to consider 3 scenarios: when x is greater than a, when x is greater between x and 0, a and 0, and between x is smaller than 0. Okay, in this case, we have f1 is 1 plus x minus 1 over 1 plus x minus a, right? And so if you try to compute this thing, well, yeah, you get an expression here, but let's not go there for now. You have x between a and 0, and so this is 1 over 1 plus x minus 1 over 1 plus a minus x. Right? Or and you can say this minus over 1 minus a plus x. Okay. And then if x is smaller than 0, sorry, x smaller than 0, you have f is 1 over 1 minus x minus 1 over 1 plus a minus x. Okay, so now let's study these functions. let's say this, as before, is going to be two functions. This is 1 over 1 plus x. It has a negative, an asymptote here at x minus 1, right? And the other one is has an asymptote at 1 minus a, right? An a minus 1. And suppose a is greater than 1, sorry, let's say this is this, right? And so let's say this function is going to be what? Like this, something like this, right? And then this function minus this is going to be, wait a minute, like this, right? And so let's see. So we have to sum these two things, right? And after this is a, right? So it's going to be something like this, right? The function, only this, plus this, okay? So something we have to check if this is positive or negative. If you compute the actual value of this, you have x plus 1, x minus a plus 1, and then minus a, right? So if this is greater than a and this is greater than a, then this is going to be positive, this is going to be negative, so this is going to be negative. So it doesn't matter how you sum it, you have that. Okay, let me plot this, the whole function. Okay. This is x equals a, so we're going to have something like this, starting here, like this, okay? And then if x equals a, then this is a plus 1, so this is minus a divided by a plus 1. Okay. Yeah. Okay. Good. Now let's go for the second function. This is over again. Let's say this function you can write as 1 over 1 plus x plus 1 over, and then we have x minus 1 minus a. Okay, so again we have an asymptote here at minus 1, and this asymptote is at a plus 1. Okay, and so we have what? The sum of these two functions, right? This is 1 over, this is going to be like this, and this is going to be like this, right? Something like that. This is 0, and this is y equals 0. Okay, so you have between 0 and a, okay, or something like this, and a, you have this sum between something, let's see, that you get negative, well, this is, well, positive, negative, it should go up to some value here. If you compute this thing, right, you have x plus 1 divided by x minus a minus 1 times 2x minus a. Okay, so when x is equal to a, then you have a divided by, and then we have a plus 1 times minus 1, so minus a times minus 1. So you have, this is continuous here. When x is equal to 0, you have, let's say, when x is equal to 0, you have minus a divided by 1 divided by minus a minus 1, or in other words, the other way around. So you have here, right? And you can check that this goes to 0 at x equals a halves, right? And if you compute this is x equals 0, sorry. So if you compute the convexity and everything, you see that this thing is going like this thing is going, so this is convex, this is concave. There's a point if you compute the second derivative here in which you can see that there's an inflection point, okay? So first you start going concave, like this, and then concave. Okay, you have a okay. Another way to see is that yeah, this function is going to be symmetric around x minus, I think so, yeah, x in between this interval is going to be symmetric respect to x equals a half, but yeah, it's easier to compute if you just compute the second derivative. Okay, and then yeah, let's see what happens with that. This is 1 over, let's see, 1 over 1 minus x, or in other words, minus over x minus 1, and then you have plus 1 over x minus 1 minus a. So you have this at x equals 1, and minus that is going to be like this, and you have this sum, which is at a plus 1, and then you have this, right? So let's see, this basically, when x is equal to 0, x is smaller than 0, this is just positive, something that's positive minus something that's not going to be smaller. If you compute in order to compute this, you have to get to the same denominator, and you have x minus a minus 1, and here you have a, right? So when x is 0, which is what we want, this is going to be minus 1, and then times minus 1 times 1, so this is equal to a, as we know. No, sorry, minus 1, this is going to be a divided by a plus 1, okay, just like this. So this is continuous, and this stands to reason because the absolute value function is continuous, right? So you just this is a decreasing function like this, we know it's going to be like that, okay? So that's what this function looks like. Okay, let's do part 4. Okay, so let's do part 4. F is x times the square root of x squared minus 1. Okay, so the domain of this is obviously whenever this is greater or equal than 0, we have this parabola x squared minus 1, right? And so this is going to be greater than 0 whenever x, the absolute value of x actually is greater than 1. Okay, so the domain is starting at 1 here, right, and at minus 1 here. Let's say plus 1, minus 1. Okay, now we know this is going to be, let's say this is going to be positive, always positive. So positive whenever, yeah, this is an odd function, as you see, right? So if we compute only the positive side, we're fine, right? Now the absolute value, the limit when x goes to infinity of this is infinity, so this is going to be like the increasing, right? It's always positive, something like that. Okay, so how does it behave? Well, there's a trick here, and we want to use Taylor. Okay, so we can actually get and a common factor x squared, right? And this is equal to x times the absolute value of x times 1 over 1 minus x squared. And remember that whenever you take this x outside, it's going to be the absolute value of x, because if x is negative, right, this is going to be minus x, okay, because this is going to be positive. The square root of a negative of this, the square root of the square of a negative number is a positive number. Okay, now what happens with this? Well, now we know that 1 minus t, right, it's going to be 1 minus t over 2 plus small o of t, when t is very small. Now if t is equal to 1 over x squared, we can apply this approximation here. So we have x times the absolute value of x times 1 minus, and then we have t, which is 1 over x squared, divided by 1 over 2x squared, plus small o of t times x. Well, this is it's going to be small o of 1. So if x is going to plus infinity, this becomes f becomes x squared times 1 minus 1 over 2, right? So this is a parabola that starts at here, something like that, at minus 2, and something like this, if I ever learn how to plot. Okay, so this function is going to be like this, and then it's going to follow this parabola up to infinity, and the same with the negative side. You're going to see, because this is an odd function, it's going to be like that, right? So if I ever knew how to paint, okay, so this function is going to be like this. Let me erase this. Okay, so we have that. Okay, something like this, behaving like a parabola. Okay. Okay, now let's go for part 5. Part 5. This is the arctangent of the logarithm of x squared minus 1. Now, what's the domain of this? Well, for the domain of the arctangent is the real line, so we don't care about this. But the domain of the logarithm is the positive number, so x squared minus 1 has to be different than 0, right? Because this is an absolute value. Okay, this is 0 exactly at plus minus 1, so we're gonna have at minus 1 and 1 we're gonna have some singularities, right? Now the range of the arctangent is between wait a minute, this is between pi over 2 and minus pi over 2. That's the definition of the arctangent, right? Now when this is going to minus infinity, right? So when x is getting close to 1 or minus 1, this logarithm 0 minus infinity, the arctangent of minus infinity is minus pi over 2. Well, this is the limit when x goes to minus infinity. So this is minus 1 and this is plus 1. You would get a discontinuity here. Right, so that's where the function is going to go. Now what happens at 0, for instance? We have, well, the only root here of the logarithm is at 0, right? The only thing that makes this 1 is 0. And so, no, sorry, this is not the only root. You have the absolute value of x squared minus 1 equals 1, or 1 minus x squared equals 1. Okay, so it's either x squared equals 0 or x squared equals 2, or that means that x is either 0 or plus minus the square root of 2. So we have 3 roots here, one here, and one here. Again, realize that this function is even, so we just need to check the positive positive half axis. So now when x is between 0 and 1, this argument is going to be negative, right? Because that parabola is growing. Yeah, so this is smaller than this is smaller than, wait a minute, 0 minus 1, when you start increasing this, then you have something that's between 1 and 0 when it reaches 1, right? So this is going to be decreasing like this. Okay, you can check the concavity computing the second derivative of this, but there's no need here. And then when x becomes positive, greater than 1, then this is going to be positive, and wait a minute. Yeah, so positive and negative until you get to the square root of 2. So you have something like this, and then this, after that, it increases from 0, the logarithm of 1 to infinity. So the arctangent of that is going to be like this. Okay, and then the same thing here. So you have this and like this, if I ever learn to paint. so symmetrical function, and you need to check that the derivative at 0 is actually there's no discontinuity at 0, so the arctangent here is going to be 1 over the logarithm of the squared the absolute value of x squared minus 1 squared plus 1, and then times the derivative of this, which is 2x divided by x squared minus 1. And so at 0, we have f prime at 0. This is going to be 0, so we have 1, 0. So the derivative at 0 for both sides, so it's okay. Okay, so this is going to be differentiable at 0. Okay, so that's it. Let's say the last part, part 6. Part 6 is f is 2 times the arctangent of x plus the arcsine of 2x over 1 plus x squared. Now, the domain of the arctangent we know is a real line, but the domain of the arcsine is between minus 1 and 1, right? Because the maximum value that the sine takes is, or minimum is minus 1, maximum is plus 1. So we have to check what's the domain. When is 2x divided by 1 plus x squared between these two values, right? Well, if you do that, you have minus 1 minus x squared smaller or equal than 2x, smaller or equal than 1 plus x squared, right? And if you subtract minus 2x in both sides, you have minus 1 minus 2x minus x squared smaller or equal than this, and this is 1 plus minus x squared minus x 2x plus x squared, but this is x minus 1 squared, and this is always greater or equal than 0, and this is minus x plus 1 squared, which is always smaller or equal than 0. So this inequality is fulfilled always. So it doesn't matter what value of x you input, the arcsine is going to be between minus 1 and 1. So the domain of this function is the real line. Okay? Now, what happens with the derivative, for instance, of this? Let's say, so we have, well, this is obviously going to have 0 at 0, right? So the arctangent at 0 at 0, the arcsine at 0 is going to be 0 as well. So this let's say the 0 of this function is at 0. Okay, so let me write this here. And also, realize that this function is, again, it's also odd. So the arctangent of minus x is minus the arctangent of minus x, and the arcsine of minus x is going to be minus the arcsine of minus x, and this function is also odd. So we only need to check the positive half axis. Now what happens, let's say the limit when x goes to plus infinity of f, you have the limit of the arctangent, which is 2 pi halves, so 2 times pi halves is pi, and then you have, let's see, the arcsine of, and this is going to infinity, and this is going to 0, the arcsine of 0 is 0, so the limit when you go to infinity is pi, so something like we have a positive asymptote here, and then a negative asymptote of minus pi for the negative limit, right? And so let's see, we have f prime, let's compute the derivative. We have 2 over 1 plus x squared, and then the derivative of the arcsine is 1 over the square root of 1 minus 2x divided by 1 plus x squared, and then multiplied by the derivative of this. Let's write it like this. And if you do this, you'll see that you get 2 divided by 1 plus x squared, and then 1 plus 1 minus x squared divided by 1 minus x, the absolute value of 1 minus x squared. Okay? And this has to do with this thing here. Now, so this is depending on if x is greater or smaller than 1 in absolute value. So we have if let's see how to say this. If x is smaller than the absolute value of 1, then you have this is 1 minus x squared. This is 1, so this is 4 times over 1 plus x squared when the absolute value of x is smaller. Okay, so this is going to be a change in the derivative here at x equals 1 and at minus 1, of course. And when you have the absolute value of x is greater than 1, so for instance think about wait a minute, greater than 1, right? This thing becomes x squared minus 1, and so you have to sum this. This is x squared minus 1 divided by x squared minus 1 plus 1 minus x squared. Then this parenthesis becomes 0, so this is 0. So there's a discontinuity in the derivative, and you have a 0 here at 1 and a 0 here at minus 1. So what happens at that point, the discontinuity at 1? What happens at 1? F at 1 is 2 times the arctangent of 1, which is pi over 2, right? This is pi over 4 times 2. And this is, when this is 1, this is 2 divided by 2, 1. The arcsine of 1 is pi over 2 again. So this is pi. So that it means that you have this, and then you have this. So at 1, you reach the asymptote, and then it's constant after that. Okay, so this function is constant after this, and then before this. And in the meantime, you have like this growth divided by this, so it's you can plot this like this, okay, it goes something like this, okay, because the two functions go like this. Okay, so you have that.